Okay, everyone, let's begin then. So we were doing permutations and combinations, and today we want to do some more practice questions. There were some questions that I specifically asked you to attempt for today's class. I will start with some of those first of all, and then we will have a look at any other questions as well that you have problems in from anywhere, from any of the worksheets or from any of the recent papers. But let's start with some of those questions that I asked you to do for this particular class. So there were two questions from this worksheet. First of all, question number 10 and question number 14, right? These were two questions that I asked you to attempt for today's class. Yeah, so these were two questions. Let's start with 14 first of all, and then we will do question number 10. And there's something that we want to compare between the two because we will be using different methods for these. And we want to understand why that would be the case. Let's start with question 14 first of all, and then we do 10 after that. Okay, question number 14. This is from May, June 21, paper 5, variant 3. Question number 6. Let's try this. Okay, so it says, how many different arrangements are there of 11 letters in the word requirement? Now, the first part is fairly straightforward. You have 11 letters in total. In how many ways can you arrange 11 letters? If there were no repetitions, you would say that's 11 factorial. But then you see, yeah, we will do 73 as well. We'll do 73 as well. Okay. So 11 factorial because there are 11 letters in total. Then we look at how many letters are repeated. R, we have two R's here. So we divide by 2 factorial because of that. And then we have an E here, another E here, another E here. So we have 3 E's. We divide by 3 factorial because of that. And what else? Q, U, I, M, N, T. Okay, so there's nothing else that's repeated. So that should give you the result. You can see what that is. That's 3326400. Okay. I would really appreciate if more of you can do these calculations. Otherwise, sometimes there end up being careless errors. So if multiple people have the same answer, that would kind of confirm the calculation as well. Okay, so that was the first part, fairly straightforward, easy 2 marks. Now it says, how many different arrangements are there of the 11 letters in the word requirement in which the 2 R's are together and the 3 E's are together? Okay, so now we want the 2 R's together and the 3 E's together. These are the only letters that are repeated. So what we can do is we can put them in a single box. So remember that representation that we used to use for this. We have 11 letters in total. So we can say we've got 11 boxes like this. Right? Initially, we would have 11 boxes that look like this. Now, the 2 R's have to be together. If the 2 R's have to be together, we merge 2 boxes and we put the 2 R's in that single box. Then the 3 E's have to be together. We merge 3 boxes, 1, 2, 3, and we put 3 E's in this box. And now the other letters are all different. There's no repetition in the remaining letters now. Okay. And how many ways can you arrange this now? How many boxes do we have? 1, 2, 3, 4, 5, 6, 7, 8. There are 8 boxes in total. And how many ways can you arrange these 8 boxes? 8 factorial. What about the arrangements for R? Well, they don't matter because they're identical. Even if you were to consider them, you would say 2 factorial, but then both of them are identical. You divide by 2 factorial. Similarly, E's are also identical. You don't really have to consider their arrangements. But if you were to consider them, you would say 3 factorial because there are 3 letters, but then all of them are identical. We divide by 3 factorial. So it doesn't make any difference. We are just left with 8 factorial. And that gives you the result. You can see what that is. What's this number? You have to evaluate this and then write down the answer. You can't just leave it as 8 factorial. What do we get? 40320. This is what we get from this. 40320. All right. That's the number that we get from this. Okay. All right. Let's look at part C now. It says, how many different arrangements are there of the 11 letters in the word requirement in which there are exactly 3 letters between the 2 R's? Okay, so there have to be exactly 3 letters between the 2 R's. This is the type of question that you will see a lot of times in recent papers. It's coming again and again, where they want you to have a certain number of letters between 2 given letters. So again, we have 11 boxes in total, right? That's how we can start. Initially, that's what the situation would be, that we have 11 boxes in which we can place 11 letters. And they would look like this. Now, they are saying there should be exactly 3 letters between the 2 R's. So we have 2 R's in total, right? We need to have 3 letters between the 2 R's. So we should have a big box like this that has 5 letters in total. So we merge 5 of these boxes. 1, 2, 3, 4, 5. Let's merge these boxes. In this big box, what we do is we say we need to have the 2 R's on both sides, and then in the middle you have 3 letters. Okay, in the middle you've got 3 letters. That's what it is going to look like. All right. Now, in how many ways can we arrange this given this condition? That's the question. Okay. So how do we think about this now? One way to do this could be that you could say, how many boxes do we have? How many outer boxes do we have? 1, 2, 3, 4, 5, 6, 7. We've got 7 outer boxes right now. Okay. And how many ways can you arrange those 7 outer boxes? You can arrange the outer boxes in 7 factorial ways. Although in this case, since we have the 3 E's identical as well, okay, let me use the other method first, because I think that's going to be easier in this case, because otherwise we have 3 E's, we might end up having a problem arranging with those 3 E's. Okay, so I'm going to use the other method that we did. Let's start with that first, the other method that we did. So we did 2 methods for questions like these, and I'll tell you why I'm not using the first one after this. So one possible way of thinking about this is that you say, you have one big box like this. This is one big box. Okay. And then these, we have 3 boxes between the 2 R's in which we can input any of the remaining 3 letters. Let me write down what the remaining 3 letters, what the remaining letters are in that word. So we have E, Q, I, E, M, E, N, T. So that's 1, 2, 3, 4, 5, 6, 7, 8. We have 8 remaining letters apart from the 2 R's. Are we missing something? I've missed U there. There's also a U. Q, U, I, R, E. So these are the remaining letters. Okay. So one way to think about this could be that we say, let's decide the number of arrangements for these letters. How many letters can we have in these boxes? 1, 2, 3, 4, 5, 6, 7, 8, 9. These are the 9 remaining letters. And how many ways can we arrange those 9 letters in these remaining boxes? We can arrange those 9 letters in 9 factorial ways, but then out of them, E's are identical. So we divide by 3 factorial because of that. So what we're doing is we are placing 9 letters, the remaining 9 letters in these boxes. In how many ways can we arrange those 9 letters? In these 9 places, 9 factorial ways. But then 3e's are identical. We divide by 3 factorial because of that. That takes into account the number of possible arrangements of these 9 letters. Okay. And now this one big box that we've got. We have considered one possible position for this, that is its current position, such that it's on the extreme left and the remaining 6 boxes are on the right side. Now, in how many ways can you move this box around? So this box is right now in its current position. Another possibility could be that it moves here, right? Such that this one box, this ends up being on the left side. And then you have this big box and then 5 boxes on the right side. That's another possible position for that big box. It could also come here. Then it could come here, here, and so on. How many different possible positions do we have for that big box? Its current position, that is 1. And then 2, 3, 4, 5, 6, 7. 7 positions. We have 7 positions for this big box. So we multiply this with 7 for that reason. And that's going to give us the result. You can see what that is. 9 factorial over 3 factorial times 7. What do we get from this? What do we get from this? 423360. Okay. 423360. That's the result that we end up getting from this. All right. Now, you're saying, why are we not multiplying by 7 factorial? We discussed this the other day as well. Remember this 9 factorial, it already is taking into account the possible arrangements for all of these letters. The letters that are going to come in these 6 boxes and in these 3 boxes. So those 9 boxes, their arrangements are already taken into account. Okay, we are not considering them in the second case. We have already taken them into account. But then once we have arranged those remaining 9 letters, now we are saying, now we're trying to figure out this big box that we have, in how many positions can this big box be? This is its current position. It could go in 1, 2, 3, 4, 5, 6 other positions. So 6 plus the original position, that's 7 positions in total. So we multiply this by 7 for that reason. 7 factorial would be, if you were to arrange the remaining boxes with this as well. We are not arranging the other boxes. We have already done that in this 9 factorial. So that will be arranging the same boxes twice. We should not be doing that, right? We have already arranged the remaining 6 boxes. Yes, exactly. So we have arranged the remaining boxes, as in this 9 empty boxes that you see here. We have already arranged them, in which those remaining 9 letters are going to come. Now we just need to think about the possible positions for this big box. Okay. Now this big box can go in 7 different positions. So we multiply by 7 for that reason. Okay. We multiply by 7 for that reason. Is that all right? Okay. I'll have a look at that. That was part C. Now let's look at part D. That's the one that I actually want to focus on, because now this is something that is going to be done one way in this particular question, but then a very similar type of problems, very similar type of statement in another question, we will deal with that in a slightly different way. And we will understand why we do that using this example now. Part D, it says 5 of the 11 letters in the word requirement are selected. 5 of the 11 letters are selected. Selection means we're talking about combination, right? We're doing selection now. 5 letters are selected out of 11. How many possible selections contain at least 2 E's and at least 1 R? Now remember, how do we used to deal with problems like these? We talked about this in our second class when we talked about combinations. Combinations cannot deal with repetitions directly, right? In this case, we have repeated letters. If we want 5 out of 11 letters, we can't just do 11C5. That's not going to work. In fact, in this case, we also have some conditions that we need to meet. But in general as well, even if there were no conditions, we could not just do 11C5. That would not work. What we need to do in such problems is we need to make cases for the repeated letter. Which letters are repeated here? We've got E's that are repeated. There are 3 E's that we have. And then we have 2 R's as well. Okay. So if you remember, we did this when we discussed combinations, that in combinations, identical objects, they cannot be handled directly. We need to make multiple cases for the identical object, right? And we did examples like this for this, right? So it's very similar to that. We will need to make cases for R's and E's, okay? But there's a condition that we've got as well. The condition is that we need to have at least 2 E's and at least 1 R. At least 2 E's and at least 1 R. Let me write that down here. At least 2 E's and at least 2 R's. At least 1 R. That's the condition that we have. And how many letters do we want to select in total? 5 letters in total. Now let's make cases that satisfy this condition. Okay, now what are the possible cases going to be? So we need cases for E's and R's, right? Because they are the repeated letters. E and R. Okay, so one possible case would be that we have 2 E's and 1 R that satisfies the condition, right? We have 5 letters to select in total, 1, 2, 3, 4, 5. Now, we are already going to have an E there, another E there, and an R there. The option is only for the remaining 2 letters. Out of the remaining letters now, what are the remaining letters? Let me write them down on the side as well. Apart from R and E, what are the remaining letters that we've got? The remaining letters are Q, U, I, M, and T. We've got 6 remaining letters that are not repeated. So in these 2 places, we want 2 out of these 6 letters. In how many ways can we do that? 6C2. So out of the remaining 6 letters, we have to select 2. So the number of possible cases that we have for the first, number of possible combinations that we have for the first case is 6C2. Okay? Because we have 2 E's and 1 R. Out of the remaining 6, we have to select 2. Okay, what are the other possible cases going to be? With 2 E's, what are the other possibilities? With 2 E's, I could have 2 R's, right? That could be another possible case. So we have 5 places. In those 5 letters, we have 2 E's and 2 R's now. So we have place for one remaining letter now. Out of the remaining 6 letters, we say we have to select one, so that becomes 6C1. Okay. Then what other case can we have? Do we have another case with 2 E's? With 2 E's, we don't have any other possibility, right? We could have 1 R or 2 R's. If we have 0 R, that would not satisfy this condition. Okay, so with 2 E's, we don't have another case. Another possibility could be that we have 3 E's. With 3 E's, we could have 1 R. That could be another possibility. 1, 2, 3, 4, 5. That means we want 1 E, and another E, another E, and then an R. And we have 1 place left. So out of the remaining 6 letters, we have to select one for this place. Okay, do we have another possibility? We could have 3 E's and 2 R's. That also satisfies the condition. So 1, 2, 3, 4, 5. We have E, 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 R, R. There's no space left now. So out of the remaining 6, we have to select nothing, 6C0. So it's either the first case or the second case or the third case or the fourth case. What we do is we add up all of these possibilities because there's an or between them. What's the result that we get from this? 6C2 plus 6C1 plus 6C1 plus 6C0. You can see what that is. 6C2 is 15, 6C1 is 6, 6C1 is 6, 6C0 is 1. 15 plus 13, that is 28. That's the number of possible combinations that we get that satisfy that given condition. Does that make sense? Why not 4 E's and 1 R? Because we don't have 4 E's. There are only 3 E's. 1, 2, 3. We don't have 4 E's. Right? There are only 3 E's and 2 R's. Okay. So that's a good question. So you're saying, are we not going to select the E's as well and the R's as well? Does that really matter? So we have 2 E's in the first case. There are 3 E's in total. You are saying we should also be doing 3C2 to select those 2 E's out of the 3 E's. Now the E's are all identical, right? There's no difference between the E's. So it doesn't really matter which 2 we select. They're all the same, right? So even if we had, if we had the first E and the second E, as compared to if we had the first and the last E, does that make any difference? It doesn't make any difference. So we don't have to select the E's and the R's in this case. They don't matter because they're identical. Okay. Okay, so if the question did not have any condition given, so if the question did not say you want at least 2 E's and at least 1 R, if there was no condition like that, in that case, you would have to consider all the possibilities, right? In this case, we are only considering 4 cases because they satisfy that given condition. But if that condition was not there, then you would have a lot of other cases as well. So you would have 0E, 0R. With 0E, you could have 1R. With 0E, you could have 2 R's. And then with 1E, you could have 1R. With 1E, you could have 2 R's. And then with 2 E's, sorry, with 1E, you could also have 0R, by the way. So that's another case. And then with 2 E's, you could have 0R. With 2 E's, you could have 1R. And then the other possibilities would be similar: 2 E's, 1R, and then 2 E's, 2R. And then with 3 E's, you can have 0R. With 3 E's, you can have 1R. With 3 E's, you can have 2R. So you would have to consider all of these possibilities and then add them up together. There's no way to do it directly. You will have to make cases, right? But in this case, since we had conditions given, that only leaves us with these 4 cases. All right, okay. So that was part D of this. Let's move on to the next one now. This was question number 14. Let's look at question number 10 now. Question number 10. Let's try this. Okay, so it says, find the total number of different arrangements of the 8 letters in the word tomorrow. So what would that be? First part, easy, 2 marks. There are 8 letters in total, so that's 8 factorial divided by, we've got 3 O's and then 2 R's, right? 3 O's and 2 R's, so we say 3 factorial and 2 factorial in the denominator. What's the result that we get from this? First part, 3360. Okay, so that's what we get in the first part. Okay, so that was fairly straightforward. Now the second part says, find the number of arrangements of the 8 letters in the word tomorrow that have an R at the beginning and an R at the end, and in which the 3 O's are not all together. Not all together. Does that remind you of something? Which method would we have to use for this? There were two methods that we did for separating objects, total minus together, and then the dashes and stars method. Which one is going to work and which one is not going to work? We're talking about three O's here. So it's not both methods that will work. For separating two objects, we could use both methods, right? But for separating more than 3 objects, it depends on what exactly we want to do. So it says not all should be together. That means 3 O's together, that is not allowed. But 2 O's can be together, okay? It is possible that 2 O's are together. So in cases like these, we use the total minus together method, the dashes and stars method. That would not work in this particular case. Okay. If they said none of the O's are together, in that case, we would have had to use the dashes and stars method. Okay. Okay. So how do we think about this now? So there's one condition that there should be one R at the beginning and one R at the end. So that condition is going to be there. Let me represent that. So we have one R at the beginning, one R at the end. Let me represent that. So let's say we have 8 boxes like this. We have an R here and an R here. Now these R's are fixed. They cannot change. There are only 2 R's and they are fixed in these positions. Their arrangements with each other also do not matter because the R's are identical. It doesn't matter which R is at the beginning, which R is at the end. That is not important because they're both identical. So R's are fixed. Okay, they're not going to change. So we only focus on the middle 6 letters. Okay, we only focus on the middle 6 letters. The R's are not important. Now, what are the middle 6 letters? P-O-M-O-O-W. Okay, so these are the middle 6 letters. We want the 3 O's to be not all together. Now, let's say we have them all together. Let's find that case first, where the 3 O's are together. What do we do for that? We put them in a single box. O, O, O. And then in the remaining boxes, we have T, M, and W. In how many ways can we arrange these? Remember, R's are fixed. They are not going to move. So this box is fixed. That's not changing. This box is also fixed. That's also not changing. Okay, so we're not going to worry about them. Just focus on these. We have 4 boxes. In how many ways can we arrange them? 4 factorial ways. That's 24. The arrangements for O's do not matter because they're all identical. So we're not going to multiply by 3 factorial because even if we do that, we would have to divide by 3 factorial because they're all identical. So it's just 4 factorial. That's 24. This gives us the number of arrangements with all 3 O's together, right? This is that case. Number of arrangements with all 3 O's together. That's 4 factorial. Okay. Now we need to find the case where there is no restriction. So we can subtract 24 from that. If there is no restriction, what would that mean? The restriction on R is still there, right? R's are still fixed, right? R's are still fixed. They're still not changing. In the middle, we have these 6 letters now. In how many ways can we arrange these 6 letters? Number of arrangements. My writing is getting worse every day. number of arrangements with no restrictions. Okay. No restriction on O's. Okay. There's no restriction on O's. R's are still fixed, right? They're not changing. In how many ways can we arrange them? There's 6 boxes, 6 factorial, but 3 of them are identical. We divide by 3 factorial. Because of that, 6 factorial is 720. 720 over 6. That's 120. That's the total number of arrangements. What do we do now? Total minus together. And that gives us 120 minus 24. And we get 96 arrangements in which the 3 O's are not all together. Okay, no problems? No problems. Fairly straightforward, right? Okay. This is June 21, paper 5-2. Question number 10 from the worksheet. Let's look at part C now. 4 letters are selected at random from the 8 letters of the word tomorrow. Find the probability that the selection contains at least one O and at least one R. Now, it's very similar to what we did in the previous question. The difference is here we were looking for the number of possible selections, right? And now they have asked us for probability. Okay, we're not talking about selections anymore. We're talking about probability of having a certain selection. Okay, so how do we how do we do this now? Part C. The word is tomorrow. We want to find the probability that there is at least one O and at least one R in the selection. That's the condition. At least one O and at least one R. That's the condition. Now, what's the probability formula? Number of favorable outcomes. Number of favorable outcomes. That is going to be divided by the number of total possible outcomes, right? So number of favorable combinations divided by the total number of possible combinations. Okay, now, if we were to do it the same way as before, how would it work? We have 2 letters that are repeated, right? We have 2 R's and then we have 3 O's. These are the repeated letters. So we make cases for them. Okay. Now don't copy this yet because what I'm going to do now is it's actually not correct. Okay. But there's a reason why I want to show this to you. If we do it the same way as we did in the previous question, we made cases like this. Let's do it the same way as the previous case and see what we get from that. How many cases do we have? Let's start with them. Let's start writing down all possible cases because remember, we want probability. So we also want the total number of possible combinations. So what would be the total possible combinations? We would get something like this. 0 O. Okay, that's going to look weird. Let's write no O and no R. Is that possible? If we want, how many letters do we want to select? We want to select 4 letters in total. Okay, we want to select 4 letters in total. 1, 2, 3, 4. If there's no R and no O, we can't have 4 letters because the remaining letters are T, M, and W. Okay, so with no O and no R, we can't have that condition met of selecting 4 letters. So we can't have this case. One possible case would be that we have no O and 1 R. Okay, with no O, you can have 2 R's. Then with 1 O, you can have 0 R. With 1 O, you can have 1 R. With 1 O, you can have 2 R's. Then with 2 O's, you can have 0 R, 2 O's, 1 R, 2 O's, 2 R's, 3 O's, 0 R, 3 O's, 1 R, and then 2 O's, 1 R, 2 O's, 2 R's, 3 O's, 0 R, 3 O's, 1 R, 2 O's, 1 R, 3 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 O's, 1 That's it. These would be all the possible cases, right? These would be all the possible cases. Now, out of them, how many satisfy the condition? How many satisfy the condition? There has to be at least one O, at least one R. Okay, so these cases would be at least one O and at least one R. So this is one possible case that satisfies the condition. Another, then another, another, and another. These highlighted cases are the ones that satisfy the condition. So we could find the possible combinations for these cases. For instance, one of them, if we were to do it the same way as before, might look like this. For the first case, for instance, if we have one R and then three remaining letters, so out of the three letters, we want three. So this would be 3C3 if we were to do it the same way as before. And then two R's and two other letters, that would be 3C2 and then 3C2 because we have one R, no 3C3 here. And then one O and one R, this would be 3C2 and so on. If we were to do it the same way as before, and if we were to find the possible combinations of these highlighted cases and then divide them by the total number of possible combinations, we would get some number, but that would not be correct. That would be incorrect, right? If we were to do it exactly the same way as before, as in the last question, where we found number of selections, that's what we do. That's what we're doing there, right? If we were to do it the same way, that is not going to give us the correct answer. Now, first of all, let's understand why that's the case. Let's consider a simple example for that. Let's say I have to find the probability. Find the probability or let's do something like this. Two letters are selected. Two letters are selected from A. So I have like 6 A's here. And then BB. Two letters are selected from these 10 letters. Okay. We want to find the probability that both selected letters are B's. Okay. Now, let's write down the possible combinations that we can have. What are the possible combinations that we can have in this case? One possible combination would be AA. Another possible combination would be AB. And another possible combination would be BB. So we have three possible combinations that we get. Okay. That's what we were trying to do here. We found the total number of possible combinations using this. But then out of them, how many satisfy that condition of both of them being B? One of them satisfies that condition. So we might say the probability of both the letters being B is going to be 1 out of 3. Why? Because we have one possible combination that satisfies the condition. And then the total number of possible combinations, the total number of possible outcomes, they are 3. So the probability becomes 1 out of 3, right? But that would be wrong. Why? Because it's pretty clear, it's pretty obvious. If we have 10 letters, there are only 2 B's in them, right? What's the probability that if you were to randomly select 2 letters from these 10 letters, that both of them are B? Does that make sense that the probability is 1 out of 3? Compare that with probability of getting 2 A's. What would that be? There's only one possible combination that satisfies that condition as well. This probability also turns out to be 1 out of 3 in this case. Can they both be equal? That does not make sense because there are much more A's as compared to B's in that original word. So it would not make sense that probability of getting 2 A's and the probability of getting 2 B's is the same. Now, the reason why it's not working is the formula that we have, the number of possible outcomes, number of favorable outcomes divided by the total number of possible outcomes, the formula that we use in probability, this formula, This formula assumes that each outcome that we are talking about is equally probable. Each outcome should have the same probability. That's when this formula works. Each outcome should have the same probability. So, for example, when we talk about rolling a dice, we have 6 possible outcomes. All of those possible outcomes are equally probable. If we consider this case, randomly selecting an A from this, the probability of that is much higher than randomly selecting a B from this. So selecting an A and selecting a B, their probabilities are not equal. So that probability formula, if we do it directly like this, number of favorable outcomes divided by the total number of possible outcomes, that is not going to work. Okay. So what else can we do then if this doesn't work? AA has a much higher probability than BB, right? So that's the problem. Okay. So we have identified what the problem is. Now, in order to make the probabilities the same for all possible outcomes, the idea is we treat all the letters as different. We treat all the letters as different. So in order to work with this, we consider all of these letters as different. We say this is A1, A2, A3, A4, A5, A6, A7, A8, and then B1 and B2. These are 10 letters in total. And we're assuming that all of them are different letters. All of them are different letters. Now, if all of them are different, then what's the probability that what's the probability of selecting two Bs? The total number of possible combinations in this case, what would that be? The total number of possible combinations would just be 10C2. That you're randomly selecting two letters out of 10 letters. If they're all different, then 10C2 will work. The combination notation is going to work in that case. And then how many outcomes satisfy that given condition? There's only one possible outcome where both of them are B's. That's the only possible outcome that satisfies that condition. So the probability for this is just going to be 1 out of 10C2. And that's going to make much more sense because the probability of B is supposed to be much smaller like this. Okay, just give me a second. 10C2, can someone tell me what that is? Okay, it's working now. 10C2, this actually turns out to be 1 out of 45. So the probability of both being B's is actually just 1 out of 45. It's not 1 out of 3. Okay. Now that's the intuition behind it. Now I understand it's quite complicated, the logic behind it. So what I'll do is I'll tell you the takeaway from this. Okay, I'll tell you the takeaway from this. That's okay. We can discuss it at the end again if you want me to explain this logic again. But let's get to the final result from that, okay? Because that's what you will actually be using in the exam now. We can talk about the logic again later on. When they ask about probability, in a combination question in which you have some repetitions. Let me write that down here. So when they ask you to find probability, that's one condition. They're asking for probability. And number two, you have combinations, right? They're asking you to select some letters. And number three, there are some repetitions. We have some repeated letters, repeated objects. In cases like this, what you do is you treat all letters as different. You treat all letters as different. Why? We do that to make the probability of all outcomes the same. Okay, if we want the probabilities of all outcomes the same, only then we can use the probability formula. For that, what we do is we treat all letters as different. Okay, I'll just remove this as well so that you just focus on what you have to do. You treat all letters as different, okay? Because we want to equalize the probabilities. Otherwise, we cannot find probability. We cannot use the probability formula without that. Now, what does that mean? We've got the word tomorrow. We have three O's. We treat all the O's as different. So we say this is O1, this is O2, this is O3. We have two R's. We treat the two R's as different. We say this is R1, this is R2. Now, if all the letters are different, what are the total possible combinations going to be? If all letters are different, and what we have to do is, we have to select 4 out of 8 letters. If there are no restrictions and all the letters are different, it would just be 8C4. That will be the total number of possible combinations without any restrictions. So that's 8C4. And that gives me 70. That is going to be the denominator in the probability formula. Then how many outcomes satisfy the condition? What's the condition? We want at least one O and at least one R. Okay, now let's represent them like this. How many O's do we have in total? We've got 3 O's in total. And remember, we are treating all the letters as different. So we have 3 O's, and then we have 2 R's, and we have 3 remaining letters on which we have no condition. So we can just club them together. Let's call them X. The remaining letters, there are 3 remaining letters. Okay, so I'm saying X is PMW, the non-repeated letters. What are the possible combinations that I can have? I want to select 4 letters. So what are the possible cases that I can have that satisfy the condition? The condition is we want at least one O and at least one R, the probability of that. We want to find that probability. At least one O and at least one R. What are the cases that we get? One O, one R, 2 remaining letters. Okay. With one O, I can have 2 R's and 1 remaining letter. These are all the cases that I can have with one O. Let's do 2 O's. With 2 O's, I can have 1 R and 1 remaining letter. With 2 O's, I can have 2 R's and no remaining letter. And then I can have 3 O's. With 3 O's, I can have 1 R and no remaining letter. These are all the possible cases that satisfy the given condition. Now, since we are treating all letters as different, the 3 O's are also all different. The 2 R's are also different when we are finding probability. Now we would also have to select the 1 O out of the 3 O's because we are treating them as different. We're considering that the O's are all different. So the first case would be 3C1 times 2C1 times 3C2. That's the first case. Then the second case would be 3C1 times 2C2 times 3C1. Then the next case is 3C2 times 2C1 times 3C1. And then you have 3C2 times 2C2 times 3C0. And then finally, you have 3C3 times 2C1 times 3C0. You evaluate each one of them and see what that gives you. The first one, 3 times 2 times 3. Can somebody confirm these calculations as well? I'm just going to do them quickly. 3 and 3 and 2, that should be 18. Then 3 into 1 into 3, that is 9. 3 into 2 into 3, that's 18 again. 3 into 1, that's 3. And then 1 into 2 into 1, that's 2. Okay, so that's what I'm getting. Can somebody confirm this as well? You add all of these up. 18 plus 9 plus 18 plus 3 plus 2. That's 36 and 45 and 5. That's 50. These are the cases that satisfy that given condition. So the probability turns out to be favorable combinations. That's 50 divided by the total number of possible combinations. It turns out to be 5/7. and that is your final result. That's the probability. Now, notice the difference between the two questions that we just did. In the previous question, the last part, we were looking for possible selections. We were not looking for probability. Okay? We were not looking for probability. We were looking for possible selections. When we're looking for possible selections, you do not select the identical objects. Okay, so you're not going to select the two E's, you're not going to select the one R. That's the standard way of doing this, right? That we do not select identical objects because it doesn't matter which one of them appears. But when we have probability, here we have the problem. When we have probability with combinations, we run into a problem. And that is that the probabilities of the outcomes, they become different. So in order to equalize all probabilities, we treat the letters as different. So that's what I meant when I said treat all letters as different. So what that means is you would also have to select which one O you are selecting out of the three O's, which one R you are selecting out of the two R's. So you also have to do this selection in this case. Okay. So in case of probability, you would also have to select the O's and R's like this. Yes. So in the previous question, we only had to find the number of ways. In that, we do not consider the objects as different. When it's about probability with combinations and repetitions, in this case, we treat all letters as different. That's a case that you need to remember. Okay. Even if you don't understand the logic, that's something that you need to remember. With permutations, it's not necessary that you do it. In permutations, you would get the same result from both cases because in permutations, we can handle identical objects directly, right? So that's not generally a problem there. So it would not matter in permutations. You can do it directly, and that will also be fine. If you want to treat them different in permutations, when you have to find probability, in that case as well, you get the same result. In both ways, in permutations, you would get the same result. There, it would not make any difference. In combinations, it does make a difference. Okay. So you can try probability questions for permutations both ways, and you would see that you get the same results both ways. Because what happens there is, let's say in the numerator, you have something like this, 3 factorial over 2 factorial, and in the denominator, you have 4 factorial over 2 factorial. If you treat them as identical, then you would be dividing by these 2 factorials like this for the repeated letters. They would get cancelled anyway. So even if you don't consider them different, you would not have 2 factorial there. Since we are finding probability, they will get cancelled out anyway. So it would not make any difference in probability questions. In permutation, okay? But in combination, it does make a difference. How do you know when the question needs you to map out all possibilities for combinations? Well, whenever you're asked for finding number of cases of number of selections or probability in case of combinations, and you have repetitions, combinations cannot handle repetitions directly. We talked about this in our first combination class, that when you have repetitions here and you have to select some objects and you have to find probability of a certain outcome, combination cannot handle that directly. You have to make cases. In permutations, we had this rule that we could just divide by factorials of the repeated objects like this, right? We don't have an equivalent of this in combinations. In combinations, we have to just list down all the possible outcomes, list down all the possible cases. We can't do it directly. So in combinations, whenever you have repeated letters, you will have to make cases. There will not be a way to do it directly in most cases. Does that make sense? Okay, good. Now, these were two important things that I wanted to cover today. Now, let's have a look at some more questions now. Now, we'll be quick about the remaining questions now. I'll start with one that Samia was asking about first, and then we'll do 73 from this worksheet, then a couple from the other worksheet. I'm going to extend the class for as long as needed. If you think that you are getting sleepy or you have something else to do, another class to attend, you are going to be free to leave and then you can watch the recording. I'll try to upload the recording right away once it ends. Okay. I would recommend that you uh, stay until the end so that if you have any questions, you can ask them. But if you have something important, something more important, what you can do is you can leave the class and then you can watch the recording. Ideally, tonight, otherwise, early morning, so that you can then do more practice if you have not done the whole worksheet then until now. Okay, so let's do that question now. What Samia asked about. Can you please tell me the question number, the paper number again? Okay, November 21, paper 5-1. November 21, paper 5-1. Okay, so that's this one, right? Okay, let's try this. Question number 7 from this worksheet. Okay, Rahman and Sanjay are members of a quiz team, which has 9 members in total. 2 photographs of the quiz team are to be taken. For the first photograph, the 9 members will stand in a line. How many different arrangements of the 9 members are possible in which Rahman will be at the center of the line? Okay, so Rahman has to be at the center of the line. And there are 9 members in total. Okay, so that's the only condition that we have. Rahman has to be at the center. Let's make 9 boxes because we have 9 people, right? Rahman is going to be exactly in the middle. So let's say this is Rahman. Okay. Now we've got 8 remaining places and 8 remaining people. In how many ways can we arrange them? 8 places, 8 people. That's just 8 factorial, right? You could actually just do it directly without drawing this as well. And that will be okay. What's 8 factorial? 40320. Okay. So this results in 40320. Okay, so that's fairly straightforward. Let's look at part B now. How many different arrangements of the 9 members are possible in which Raman and Sanjay are not next to each other? Okay, that's another standard question. We have to separate Raman and Sanjay. We can either do total minus together or the dashes and stars method. Both of them will work since we're just separating 2 people. Okay, both methods work in this case. Okay, so we have 7 remaining people. Let's make dashes for them. 1, 2, 3, 4, 5, 6, and 7. Right, 7 other people. 7 factorial is going to be their arrangements. And then Raman and Sanjay, they have to be separated. They're going to come in these places in the middle. 1, 2, 3, 4, 5, 6, 7, 8. 8 places, 2 people. In how many ways can we arrange them in those 8 places? 8p2. And that should give us the result. You can see what that is. 7 factorial into 8p2. What do we get from this? 7 factorial into 8p2. Okay, 282240. Thank you. So that's what we get. That's part B. Let's look at the next one, part C. For the second photograph, so in this case, you could also do total minus together. That will also work. For 2 people, for 2 objects, both methods work. Okay. For the second photograph, the members will stand in 2 rows with 5 in the back row and 4 in the front row. In how many different ways can the 9 members be divided into a group of 5 and a group of 4? Is it permutation or combination? Are we talking about permutation or a combination? Combination, right? We're talking about grouping them. Arrangement does not matter. So we're just talking about group right now. So there are 9 people. We have to divide them into 2 groups. One group of 5 and the other group of 4. So that's going to be 9C5. So we select 5 out of those 9 people and put them in one group. And that's going to be enough, right? When we put 5 people in one group, it's understood that the remaining 4 people are going to be in the other group, right? That's kind of obvious. Or if you want to explicitly do that here, you can say select 5 out of 9 people. And then how many people are we left with? 4 people. In the other group, you would have 4C4, right? 4 out of 4, they're going to go in the other group. This is just one. So even if you don't write it, that's going to be okay. What's 9C5? 126. Okay, this is what we get from this. Yes, Ibrahim, that's correct. When it says none of some objects have to be together, you use dashes and stars method. When they say not all of some objects should be together, that means total minus together. So that is correct. However, when we're talking about 2 people, then it does not matter, right? Then you can use both of them. Okay, so that was part C. Let's look at part D now. For a random division into a group of 5 and a group of 4, find the probability that Raman and Sanjay are in the same group as each other. Okay, so how do we think about this now? We know the total number of possible combinations, that's 126. We want to find the probability that Raman and Sanjay are in the same group as each other. There could be 2 possibilities for this, right? Why 2 possibilities? Because one group has 5 members and the other group has 4 members, right? So first case could be that Raman and Sanjay, both of them are in the 5-member group. So 1, 2, 3, 4, 5. We've got 5 places in one group and we have 4 places in the other group. Let's say Raman and Sanjay are both here, okay, in the first group. Now, if they're both here in the first group, how many people are we left with? We're left with 7 people, right? Out of those remaining 7 people, we have to select 3 in this group and 4 in this group. You can start from either of them, it doesn't matter. You can say 7C3 from here. Select 3 out of 7 people for putting them in this group. Into, we have 4 people left, 4C4, right? For the other group, you have 4 people left and you have to select all of them, that's 4C4. That's one possible case. Okay, and that will give you some answer. 7C3, what's that? 7C3? 25, 35? Okay, 7C3 is 35. 35 times 1, that's 35. That's the first case. The second case would be 1, 2, 3, 4, 5. 1, 2, 3, 4. The second case is that Raman and Sanjay are in the 4-member group. That's the second possibility. Again, we have 7 people left. Out of those 7 people, we want 5 in this group now. So that will be 7C5. Then 2 left. Those remaining 2 people will go in these 2 places, 2C2. 7C5, what's that? That's 21. So it's either the first case or the second case. We add these 2 cases up. The total becomes 35 plus 21, which is 35 plus 21. That gives us 56. That's the number of possible groups, the number of possible divisions in which Raman and Sanjay are in the same group. So what's the probability now? They asked us for probability. Number of favorable divisions, 56, divided by the total number of possible divisions, 126. And that will give you the probability. You can see what that is. What do we get from this? 28 over 63. Does that simplify further? No. 28 over 63. That's the probability. Okay, if you write that in decimals, make sure to write three significant figures. 28 over 63. That's 4 over 9. Okay, that does actually simplify further. It's 4 over 9. If you write decimals, that would be 0.444. Okay. Three significant figures. And that's the final answer. Any problem with this? Is this all right? Clear to everyone? Okay, now let's do a couple of more tricky ones now, and then we end. This was 7 from the worksheet. Another that I asked you to do from the worksheet, it has a wrong answer in the marking scheme as far as I remember. Let me just check that as well. What's the, so those of you have done that, 73. I'm particularly going to do the last part. I will skip the other two, I think. Okay, let's do this. Let's do the whole question, and that's okay. Question 73. The last part is the one that I particularly wanted to do. But let's look at the whole question. It says 4 families go to a theme park. 4 families go to a theme park together. Mr. and Mrs. Lynn take their 2 children. Mr. O'Connor takes his 2 children. Mrs. and Mrs. Emmett take their 3 children. Too many names. Okay, we have Mr. and Mrs. Lynn. They have 2 children with them. Okay, Mr. O'Connor takes his 2 children, so that's 3 people. And then Mr. and Mrs. Ahmed and the 3 children, there are 5 people. And then Mrs. Burton takes her son, that's 2 people. The 14 people all have to go through a turnstile, one at a time, to enter the theme park. Okay. In how many different orders can the 14 people go through if each family stays together? Okay, now that's just a different different way of asking. In how many ways can we arrange these people if each family stays together, right? So what you do is you say there are 14 places. However, the families have to stay together. So there are 4 people here in Mr. and Mrs. Lynn family. So that's 4 people. Let's call them L1, L2, L1, L2, L3, and L4. And then 3 people in Mr. O'Connor's family. That will be C1, C2, C3. And then we have 5 people in Mr. and Mrs. Emmett's family. That would be A1, A2, A3, A4, A5. And then finally, Mrs. Burton takes her son. Okay, so B1 and B2. And how many ways can we arrange them? 4 factorial, right? 4 boxes. And then 4 factorial for the Lynn family, 3 factorial for the Connor family, 5 factorial for the Ahmed family, and then finally 2 factorial for the Burton family. And that should give you the result. That's the number of different arrangements that we can have of these 14 people. That's 829,440. Thank you. 829,440. That's the result that we get from this. Okay. That was fairly straightforward, a pretty standard arrangement question. Let's look at the second part now. Let's look at the second part now. The second part says, in how many different orders can the 8 children and 6 adults go through if no 2 adults go consecutively? Okay, now how many adults do we have? 2, 3, 4, 5, 6. We have 6 adults. Okay, yeah, they actually told us that as well, that there are 8 children and 6 adults. Okay, no 2 adults should go consecutively. That means we have to separate the adults, right? Just use the dashes and stars method. What do we not have to separate? Children do not have to be separated, so we make dashes for them. 1, 2, 3, 4, 5, 6, 7, 8 dashes for the children. They don't have to be separated, right? So that would be 8 factorial. But then in these places in the middle, we've got the six adults. How many places do we have? How many gaps do we have? 9 gaps in total. So we'll say this is 9p6, where the 6 adults come, and that's it. That gives you the result. You can see what that is. 8 factorial. Okay, can somebody tell me what this number is? That's a big number. 2, 4, 3, 8, 5, 5, 3, 6, 0, 0. That's the result that we get from this. Make sense? That was the second part. Again, pretty straightforward if you know your arrangements well. That wasn't that complicated either. Let's look at the third part now. The third part says, once inside the theme park, the children go on the roller coaster. Each roller coaster car holds 3 people. In how many different ways can the 8 children be divided into 2 groups of 3 and 1 group of 2 to go on the roller coaster? How many groups can we make from this? Now, how do we think about this? We have 8 people in total. We have 8 people in total. We want to divide them into groups of 3, 2 groups of 3 and 1 group of 2. So out of 8 people, we can say, let's select 3 for the first group. Okay. So we have a 3-member group. 1, 2, 3. 3 for the first group. Okay. Then there's another 3-member group. 1, 2, 3. You say this is from the remaining 5 people, select 3 more. And then you have to select people for a 2-member group. From the remaining 2 people, you select 2. So you multiply them. What does that give you? 560. This is not correct. This is not the correct answer. This is not going to be 560. If you've seen my video on the crocodile question, if you've understood it well, you should have gotten this correct as well. This is, again, a question that Cambridge got wrong. The first time they did it, since it's an older paper, I have not been able to find the updated marking scheme for this because it's not on the Cambridge portal anymore. But it's very likely that they would have updated it later on, just like they did for the crocodile question, because there's an error in this. Okay, this is not correct. Now, what's the error? Let's try to understand that. When we do 8C3 into 5C3 into 2C2, what we're saying is we are selecting 3 people for the first group, 3 people for the second group, and then 2 people for the third group. Let's take an example. Let's say we have people labeled like this: A, B, C. People named like this: A, B, C, D, E, F, G, H. Okay, we have people labeled this way. All right. Now, the problem here is we have two groups that both have 3 members, right? Both of two groups have 3 members each. Now, in these 560 groups, one possible grouping could be that you have A, B, C, D, E, F, G, H. This is one possible grouping that you can have. Okay. But is that the only possible grouping? No, this is one possible grouping that we can have. But let's compare this with another grouping. Let's say we have another grouping and that looks like this. Let me add some space here. We have another group that looks like this: D, E, F, A, B, C, G, H. Now, this 560 is counting these two groups as these two groupings as two different groupings. But are they really different? Are they really different? They're both the same. They're both the same because the only thing that has changed is we have put A, B, C in the second group in the second case, and we've put D, E, F in this group in the first group in this case. That's the only thing that has changed. So we have to account for the fact that since these two groups have the same size, if we switch them, if these people go here and these people go here, this 560 is counting these two groupings twice. Okay, these two are being counted twice. For that reason, we would have to divide this number by 2 factorial. This number would have to be divided by 2 factorial. That's the number of arrangements for these two groups. We divide this by 2 factorial, and this actually should turn out to be 280, not 560. Okay. So when we're doing this grouping, 8C3 into 5C3 into 2C2, what's happening is it's saying this is one possible grouping. This is another possible grouping. But they are essentially the same. There's no difference between them. The only thing that has changed is the 3 people that were in the first group earlier, now they've moved to the second group, and 3 people that were in the second group earlier, they've moved to the first group. Right? They've just switched places, but the groupings are still the same. Right? The 560 that we were getting from the numerator here, it was counting this as 2 separate divisions. Okay, but they're not two divisions. They're both the same. There's no difference between them. So in order to get rid of this repetition, in order to get rid of this double counting, we divide by 2 factorial, right? The number of possible arrangements that we can have for these same groupings, right? The identical groupings, we divide by 2 factorial because of that. And if you have seen the explanation for that crocodile question, that was much more complicated than this, but it's the same thing that we do there as well. Okay, and that was the reason that they got that wrong the first time as well. But fortunately, I have the updated marking scheme for that from Cambridge, as in they have uploaded it on their support hub. So otherwise, it's difficult to convince students sometimes because they say that Cambridge can never be wrong. But that is updated. Okay. But this question, I could not find the updated marking scheme, but it definitely is incorrect in the marking scheme. This is what it should be. Okay. All right. So this is 280. And that's the result that we get from this. Okay. How do we know that we have to divide by 2 factorial? Compare it with the previous example. In this case as well, you remember we had to do this division. We had 9 people, and we wanted to divide those 9 people into a group of 5 and a group of 4, right? That's 9C5 into 4C4. Now, in this case, since both the groups were of different sizes. One was a group of 5 and the other was a group of 4. In this case, it did not matter because they could not be identical groupings in this case. But when you have multiple groups of the same size, right? We have two groups of 3 people. That is when we have this problem that we can have double counting like this. So we have to get rid of that. Okay. So when we have multiple groups having the same size, we would have to divide by them like this. Okay. Okay, let me write that down here. We need to divide by 2 factorial. Because there are two groups having the same size. So there will be double counting if the members of those two groups switch places with each other. Okay, so that's not a very clear explanation, I think, but I think it would remind you of the discussion that we had. Okay. All right, let's move on. That was 73. Let's move on to the next one from the first worksheet now. There was one question that I asked you to do question number 25. Yeah, this is an important one. The second part of this, I'll just do the second part. First part is fairly straightforward. It's simple combination question in which you have to make cases and then add up all of those combinations. So I'm going to focus on the second part in particular. 25. Question number 25. Let's have a look at this. Okay, so what I'll do is I'll just show you the working for the first part and then you can complete that afterwards. So there are 25 flowers in a flower bed. He can choose from, Jeff can choose from 15 different geraniums, 10 different roses, and 8 different lilies. He wants to have at least 11 geraniums and the same number of roses and lilies. Find the number of different selections that he can make. Okay, so what are the total numbers that we have for each type? We have 15 geraniums, so we have 15 of these. And then we have 10 roses, and we have 8 lilies. Okay. What's the condition? We want at least 11 geraniums. Okay, so at least 11 of these. And then the same number of roses and lilies. That does not mean that they're also going to be 11. That's not even possible because if they're 11, then the total would not be, what's the total? Total would not be 25, right? So it can't be that. Same number of roses and lilies, that means that their numbers amongst themselves, they should be equal, right? So if we have 11 of these, The total has to be 25. What's the remaining number of flowers? 25 minus 11, that's 14. So they have to be split equally like this, 7 and 7. That's one possible case. Another possible case could be that we have 12 here. Now, if the number of geraniums is 12, what's the number that you're left with? 25 minus 12, that's 13. Can we divide 13 equally amongst these two types? We can't, because that will be a decimal, 6.5. We can't have 6.5 flowers, right? So this case is not possible. So the next case would be that we have 13 geraniums. If we have 13 here, 25 minus 13, that leaves us with 12. That 12 has to be equally divided amongst these two. That would be 6 and 6. And then 14 is not possible again, because that will give us decimals for the others. So we have 15 next, and that leaves us with 5 and 5. And that's it, because we have total 15 geraniums. We can't go beyond that. And that should give you the result, the number of different selections. You would say it's 15C11 into 10C7 into 8C7. And then 13C11 into 10C6 into 8C6. You have to show all of this working. You can't just write down the answer directly. It's 4 marks. This working is important. Okay, that was, okay, there's something wrong there. This should have been 15C13 and then 15C15 times 10C5 times 8C5. You'll evaluate each of these numbers and then add them up together, and that will give you the total. Okay, that's the idea that you use for the first part. That's fairly standard combination question. And this is how you could do that. Okay. Now, the second one is what I wanted to specifically discuss, the second part. Find the number of different ways in which the 9 letters of the word green gauge can be arranged if exactly 2 of the G's are next to each other. So we want exactly 2 G's next to each other. How do we do that? So we know how to do how to have all G's next to each other. We know how to separate all the G's. But what about having exactly 2 G's next to each other? How do we do this now? Now, if you one idea that might come to your mind could be that you could say that we want 2 G's together, right? Green gauge is the word. So what you do for that is you say, let's put 2 G's in the same box, right? There are 8 boxes in total initially. 1, 2, 3, 4, 5, 6, 8. We have, sorry, there are 9 letters in total. So there are 9 boxes initially. The 2 G's have to be together. So you could say, let's put them in a single box. And then the remaining letters are going to be R, E, E, A, N, A, G, E. These are the remaining letters, the remaining 7 letters. And you could do it like this. So that would be 8 factorial. But then you have some repetitions here. 1, 2, 3. 3 E's. We divide by 3 factorial because of that. And that's it, right? Will that work? Will that work? If not, what's the problem with this? Could we just do 8 factorial over 3 factorial? Eight factorial over 3 factorial. Is that going to work? What's the problem with this? What's the problem with this? The question says we want exactly 2 G's together. If we do it like this, we could also have, yes, we could also have another G in the next place. And that's not something that we want. We can't have 3 G's together, right? So we have to eliminate this case as well, where all the 3 G's are together. So this is not going to work, right? Because by accident, third G can come next to these 2 G's using this method. So this is not going to work. Okay, so how do we think about this then? One idea using what we know already from the previous methods that we have done could be We know how to separate out the three G's, right? So we can have basically three possibilities. One possibility is all G's are separate. Another possibility is all G's are together. And another possibility is that two are together and one is separated. We know how to evaluate this. We know how to evaluate this. Find the total arrangements, subtract from that all G's being separate and all G's being together. And you would be left with this case. That's one possible way of thinking about this. Let me do it this way first. So I hope you get the idea. So what you do is you can say find the total arrangements, subtract from that the case when you have all G's together, and subtract from this the case when you have all G's separated. Subtract these two cases, and that would leave you with that one case where two G's are together and the third G is not together. The third G is separated. Okay. Now, what's the total arrangements going to be for the word green gauge? That's the word, right? The word is green gauge. 9 factorial divided by, we have three G's, so 3 factorial, and then 3 E's, 3 factorial for that. And that's it. Okay, that's the total number of arrangements. That will give you some number. Can somebody tell me what this is? All G's together, we put all G's in a single box. So we have 9 boxes in total initially, right? If we want all G's together, we merge 3 boxes, put 3 G's in this single box. In how many ways can we arrange this now? The remaining letters are R, E, E, N, A, E. 7 boxes in total. That would be 7 factorial divided by 3 factorial because of the 3 E's that we have. These are repeated. And that will give us the result in this case. So the first one you're saying is 10080. And then the second one, 7 factorial over 3 factorial. Okay, all G's separated. If all G's have to be separated, we start from those letters that do not have to be separated. Apart from G's, we have 6 remaining letters, right? We start with them. We want to separate all of them, right? So dashes and stars method, that's what we can use. 1, 2, 3, 4, 5, 6. We have 6 places for the 6 remaining letters. Okay, apart from the 2 G's. They are R, E, E, N, A, E, right? In how many ways can we arrange them? 6 factorial divided by 3 factorial. And then in the gaps between the dashes, we have the 3 G's. How many positions do we have for them? 1, 2, 3, 4, 5, 6, 7. We have to place the 3 G's in these positions. In how many ways can we do that? 7 positions, 3 G's, 7 P3. But then all of them are identical. So we divide by 3 factorial. Or you could also just do 7C3. That would also work. And that will give you another result. What's this number? 6 factorial over 3 factorial into 7P3 divided by 3 factorial. That's 25200. And now we can find the number of arrangements with exactly 2 G's together. What would that be? Subtract from the total the case when all G's are together and the case when all G's are separated. And that will give you those arrangements in which exactly two G's are together. The previous one is 4,200. Yeah, so 25 to 1,200 will also actually not make sense because the total is 10,000. So that cannot be 25,000. Okay, so I should have figured that out. That's 4,200. Okay, so this is 4,200. What do we get from this? 5,040. Is that correct? 5,040. That's the final answer. This is one way of doing this that's pretty long for those 3 marks, right? That we have to find so many cases. Find the total and then subtract from that the case when all are together and then all are separated, and that gives you the result. Okay, this is one possible way of doing this. A more efficient way of doing this would be that you say, we want exactly two G's together. And the letters that we have are G, R, E, E, N, G, A, G, E. These are the letters that we've got. We want exactly two G's together. And the third G should not be next to those two G's, right? One way to think about this is we say, let's put the two G's in one box and put the third G in another box. And now the idea would be that we want to separate these two boxes, that these two boxes should not be together. Okay, put two G's in one box, one G in another box. And now if you want exactly two G's together, you want to make sure that these two boxes do not come together. So now you want to separate out these two G's, these two boxes. Okay. Now, how do we do this? We start from the remaining letters that we do not have to separate. What are the remaining letters? R, E, E, and A. These are the letters that we do not have to separate. Let's start with them. We make dashes for them. Letters that we do not have to separate. 1, 2, 3, 4, 5, 6. There's 6 of them. In how many ways can we arrange them? 6 factorial divided by 3 factorial because of the 3 E's that we've got. 6 factorial over 3 factorial. Okay. And then we have to place these two boxes in the places in the middle. 1, 2, 3, 4, 5, 6, 7. We've got 7 gaps. 7, P2. We have to place these two boxes there, right? Do we divide by 2 factorial to 3 factorial? No. These boxes are different. One has two G's, the other has one G. So these are not identical boxes. These are different boxes. So we just do 7P2. And that should give us the final result. This should also turn out to be 5,040. Okay. Has somebody confirmed this? Right? So that's 5,040. So you could do it directly like this. Okay, that's much more efficient. Any questions on this? Any questions, anyone? No? Okay. One last question that somebody asked in the WhatsApp group earlier. That was that tiles question. I'll just do that tiles part and not do the other parts. 32 it was? Okay. 32. Okay. 32 parts. Let's just do this last part. The other parts, I think they're doable. Okay, by the way, when they talk about twins, please remember twins are not considered identical. Okay, twins are not considered identical. Even if they're identical twins, they're still not identical. Okay, so don't treat them as identical people. People are never identical. Okay, they're always some differences. Okay, even if you have identical twins, you don't consider them identical. Okay, just keep that in mind because they're people. people are not identical. Okay, let's look at part C. You can do the first two parts. Now, this person, Helen, has some black tiles, some white tiles, and some gray tiles. She places a single row of 8 tiles above her wash basin. Each tile she places is equally likely to be black, white, or gray. Find the probability that there are no tiles of the same color next to each other. Okay, so she has 8 tiles in a single row. 8 tiles in a single row. 1, 2, 3, 4, 5, 6, 7, 8. Okay. And there are 3 colors that we can have. The 3 colors are black, white, and gray. We want the probability that there are no tiles of the same color next to each other. Okay, how do you find probability? Number of favorable outcomes divided by the total number of possible outcomes. What are the total possible arrangements without any restrictions? If there were no restrictions, what would be the total number of possible outcomes? You would have 3 options for filling the first box, right? You can have black, white, or gray in the first box, 3 for the second, 3 for the third, and so on. What does that give you? 3 power 8. Because there are 3 tiles, right? 3 colors that we can have. So for the first place, we either have black, we can either have black or white or gray. Right? These are the 3 possibilities that we can have. Okay. And it's the same for each box. 3 options for the first one, 3 for the second, 3 for the third, 3 for the fourth. And that gives us 3 power 8. That's the total arrangements without restrictions. That's the total arrangements without any restrictions. Okay, now what's the restriction? The restriction is no 2 tiles of the same color should be next to each other. That's the restriction. Now, if no 2 tiles can of the same color can be next to each other, how many options do we have for the first box? Again, we've got 3 options for the first box, right? We can have any of the 3. Yes, so we are randomly putting tiles, right? Each tile is equally likely to be black, white, or gray. So we are randomly putting tiles in these boxes, right? So that's why we say we have 3 options, right? Now for the first tile, we have, for the first place, we have 3 options. Now, once we have placed one tile here, so let's say we have placed any of the 3 colors here. Let's say we've placed black here. Now, if we have black as the first tile, how many options do we have for the next tile? Whichever color you put in the first box, how many options are you left with for the second box? You can't have that color again in the next box, right? So the next box only has 2 options now, because you can only have gray or white in the next box. Okay. Let's suppose we have gray here. It could be gray or white, right? Any of them. Whatever color it is, the next one again cannot be that color. So the next one cannot be gray now. It could be white or black. So how many options do we have for the next one now? 2 options. Not 1. You can have black again, right? Black is also an option. So we still have 2 options. And whatever color comes here, so let's say we've got black again. How many options do we have for the next one now? We can't have black, but we can have white or gray. So 2 options for the next one, and so on. We've got 2 options for each of those next tiles. What does that give you? 3 into 2 raised to power 7. That's the number of outcomes that satisfy the condition. What is the probability going to be? 3 into 2 raised to power 7 divided by 3 raised to power 8, and that gives you 2 raised to power 7 over 3 raised to power 7. You can see what that turns out to be. Just put this on your calculator and see what that is. Okay. That's 0.0585. That's the probability that we were looking for. Or you could write fraction as well. That's also fine. Oh, I'm getting a different fraction. Have I done something wrong here? 2/3. And then raise that to the power 7. Oh, okay, all right. Okay, so that's this part C. And that's it for today. That's it on permutations and combinations as well. That's the most difficult topic that you have in S1 and arguably across A-level paper or across A-level math papers, P1, P3, M1, S1. I think this is probably the hardest topic, integration as well. Once you've done all the concepts, it's not that difficult because there's not much that the examiner can do apart from the standard cases. But in permutations and combinations, you frequently get questions in which you have to think on your own in the exam itself. So that's what makes it slightly more difficult. Okay, so that's it for today then. I'll see you again in the next class. Yes, Ibrahim, we'll have to be very quick because it's very late for me now as well. But you can ask your questions, but let's be quick about that. Okay, everyone else, you're free to leave if you don't have any individual questions. I'll see you again in the next class. Allah Hafiz. Ibrahim, maybe I can give you some hints, and then if you are able to figure them out, that will be great. Otherwise, we can discuss them later. Okay, you can send them to me, and maybe I can just verbally try to explain what to do. And if that makes sense, you can complete those questions then. If you still have problems, we could discuss them in the next class then. Okay, all right, that's good. So you've done your working. You can send me the questions then. Gee, what about this?
In this question, I arranged it. इन्होंने देखने हैं क्वेश्चन पर तो इसके अंदर क्या नाम है जब मैंने बाइक्स को और उनको अरेंज किया है, जो एम्प्टी स्पेसेस थी उनको मैंने 5 लाइक पूरा जो बड़ा वाला बॉक्स है और एम्प्टी स्पेसेस हैं उनको मैंने 5 फैक्टोरियल से किया था, जबकि एमएस में सिर्फ
एम्प्टी
5।
एम्प्टी स्पेसेस तो आइडेंटिकल है, उनमें तो कोई डिफरेंस नहीं है ना, स्पेसेस में तो कोई डिफरेंस नहीं है, उनको क्यों अरेंज करना आपने? स्पेसेस को तो
लेकिन
अरेंज नहीं
इन
करेंगे
सब
ना।
इन सबको अरेंज नहीं करना पड़ेगा, एक पूरा बड़ा बॉक्स जो
बस
एम्प्टी स्पेसेस है।
जो बड़ा वाला बॉक्स है, बस वो अपनी पोजीशन चेंज कर सकता है ना। सो जो
अच्छा,
बड़ा वाला बॉक्स है वो जा सकता है, how do I annotate in this? ओके, तो जो बड़ा वाला बॉक्स है वो इधर लेफ्ट पे आ सकता है, फर्स्ट प्लेस पे, इधर आ सकता है सेकंड प्लेस पे, इधर, और फिर इधर और इधर. So there are five places for that big box, right? That's why you just multiply that with five, not 5 factorial.
कंफ्यूज हो जाता हूँ कि मतलब 5 फैक्टोरियल कब यूज करना है और लाइक 5 कब यूज करना है।
लॉजिकली सोचे ना, फैक्टोरियल डायरेक्टली कुछ नहीं होता, मतलब देयर इज नो लॉजिक फॉर फैक्टोरियल एज सच. फैक्टोरियल वो बन जाता है जब हम कहते हैं कि अच्छा एक चीज को अरेंज करने के 5 वेज हैं, फिर नेक्स्ट बॉक्स में 4 ऑप्शंस हैं, फिर नेक्स्ट बॉक्स में 3 ऑप्शंस हैं, फिर नेक्स्ट बॉक्स में 2 ऑप्शन है, फिर नेक्स्ट के लिए 1 ऑप्शन है. वैसे तो लॉजिक
हम्म
ये हो रहा होता है, वो 5
हम्म।
फैक्टोरियल बन जाता है फिर. तो यहाँ पे तो हमने सिर्फ इस बॉक्स को अरेंज करना है, तो उसमें सिर्फ 5 ही आएगा, बाकी सारे तो होंगे नहीं.
तो अच्छा अच्छा।
इसलिए हमने शुरू में ये मैनुअली किया था,
हम्म।
फैक्टोरियल से बगैर, ताकि आपको ये कॉन्सेप्ट क्लियर हो कि फैक्टोरियल जो है वो मतलब कोई डायरेक्ट कोई कॉन्सेप्ट नहीं है सच, वो बस नंबर्स उस तरह से लिखे होते हैं कि वो फैक्टोरियल बन जाते हैं, राइट.
ठीक है सर, समझ गया।
जी. आगे.
तो अगला भेजिए सर।
इकट्ठे सेंड करते हैं, बस मैं एक दफा यहाँ पे कॉपी कर लूँ.
ठीक है।
या इट्स ओके, ठीक है, आप मुझे मिल गया. ये वाला.
ये सर इसका फर्स्ट पार्ट। फिर जब वो इसके अंदर हमने प्लेस कर दिए जो दो थे, जॉन एंड सारा को, तो टैक्सी पी में फिर बाकी 8 पैसेंजर्स में से प्लेस करने के लिए 6C2 लगेगा, और बाकी 4 रह जाएंगे उसके लिए, अगली के लिए। तो वो 15 ही देगा, ये 30 कैसे हो रहा है, ये नहीं समझ आया।
दे हैव टू बी इन द सेम टैक्सी, राइट. उसने
हम्म।
ये तो नहीं बताया कि कौन सी वाली टैक्सी.
ओ हाँ, दो
तो
पॉसिबल।
एक केस होगा कि वो पी में है, दूसरा केस होगा वो क्यू में है.
ठीक है सर, ठीक है, समझ गया।
टू से मल्टीप्लाई करना पड़ेगा.
ओके सर। सर इसके ऊपर भी एक चीज़ भेजी थी मैंने, जो जो आपने शुरू में क्वेश्चन कराया था ना, उसकी वर्किंग जो मैंने
हाँ.
आपको कहा था। तो मैंने इसकी इस तरह की थी, आपने लाइक ई, आपने विदाउट ई को अकाउंट फॉर किया था ना, मैंने लाइक ईज को लिया था उसके अंदर, कि पहले विदाउट ई आ गया आर्स के दरमियान, फिर एक ई, दो ई, फिर 3 ई।
एक मिनट. अच्छा जी, क्या कह रहे हैं इसमें.
इसके अंदर लाइक आपने तो डायरेक्ट कर लिया था ना, तो
हम्म.
इसके अंदर मैंने ईज के सेपरेट केसेस बनाए थे, कि आर्स के दरमियान एक ही आ गया, फिर दो ही आ गया, फिर 3 ही आ गया।
ठीक
तो
है.
फिर इस तरह क्यों नहीं आंसर आ रहा सही।
और आपने नो ई वाला भी कंसिडर किया, राइट.
हाँ जी,
अच्छा,
सबसे ऊपर
वर्ड
वाला।
वर्ड क्या था, रिक्वायरमेंट है ना.
हाँ जी सर।
ओके. एंड वी वांटेड एग्जैक्टली 3 लेटर्स बिटवीन द 2 आवर्स. ओके, सो आपने एक क्या किया, आपने उसको एक बड़े बॉक्स में डाला और आपने कहा एक केस ये है कि कोई भी ई दरमियान में नहीं आ रहा. अगर कोई भी ई दरमियान में नहीं आ रहा तो 6P4, बाकी 6 में से
ये 6P3 होना चाहिए था आई गेस, है ना।
6P4 क्या कर रहे हैं.
वो लाइक जो 6 हैं, बाकी के 6 हैं, उनमें से सिलेक्ट कर रहे हैं 3
तो वो
विदाउट ई वाले।
3 है ना वो तो.
हाँ, यहाँ पे 3 आ जाएगा है।
इंटू 7 फैक्टोरियल वो 3 फैक्टोरियल, दैट मेक सेंस. और फिर 6C2 इंटू 3 फैक्टोरियल, दैट्स गुड. और बाहर आपके पास आ गया 7 फैक्टोरियल ओवर 2 फैक्टोरियल बिकॉज ऑफ दोस 2 e's. दैट ऑल्सो मेक्स सेंस. ओके. Then 6C1 into 3 factorial divided by 2 factorial. Okay, that's fine. 7 factorial. And then last one, 7 factorial because वो तीनों e's up. I think that should work. That should
एक
work.
ना मैं आंसर चेक कर लूँ। हाँ जी सर, सही आ रहा है, मतलब वो सिर्फ उसका मसला था।
या लेकिन इसमें लंबा हो रहा है ना, बिकॉज वो ईज का मसला आ रहा था इसके अंदर, कि वो
हम्म।
आइडेंटिकल थे, तो उसमें फिर कौन कितने ईज अंदर आएंगे, तो दैट वाज द प्रॉब्लम, तो केसेस बना के वो फिर इस तरह लंबा हो जाता, बट या
हाँ।
दैट्स गुड विद एक्चुअली।
ऑल ऑल राइट सर।
ओके।
सर
ऑल
बस एक बार ये देख लें कि आपकी जो वर्कशीट है उसके अंदर फिफ्थ वाला क्वेश्चन पार्ट है या नहीं है, या फिर वो अगला प्रोबेबिलिटी एंड डिस्ट्रीब्यूशन का पार्ट है।
कौन सा?
पुरानी वाली वर्कशीट में फिफ्थ क्वेश्चन।
नहीं नहीं, ये वो है डिस्क्रीट रैंडम वेरिएबल्स है, इसको छोड़
ऑल राइट। थैंक यू सो मच सर।
दो। नो प्रॉब्लम।